let's start with some of the concepts that we covered, which is pretty easy. So, I mean, when you are watching this video, this is my feeling. Just ratify my hypothesis, folks. Some of the contents that we covered right in the first session, it's a repetition of that content. Have you felt the same?
Yes.
Yes, correct.
Right?
The videos are same. Yeah, you're right.
So some of the content, essentially what we covered about what is machine learning, different types of examples of machine learning, what fits into machine learning versus what's not, what is supervised versus what is unsupervised. So I'm assuming all that because you have watched in those first videos, I tried to provide the context, and then you also watch the videos again now as part of this particular one. I am at least assuming and sensitizing that we don't need to spend too much amount of time there, but let's do a quick recap and refresh of those concepts and then quickly go on to the additional stuff. Does that make sense?
Sure. Yeah.
Right. So now first question, what is machine learning? I know Mukesh used a particular definition by Samuel, which has been in 1970s, 50s kind of a thing, but he has used one simple definition, but I try to put it in a different way. Both essentially mean the same, but what is machine learning at the end of the day for us? Okay, let me rephrase my question. What is the difference between a software program versus a machine learning algorithm?
One is based on rules totally, and machine learning is based on algorithms, which has a self-learning component.
So for writing rules and everything also, you will write essentially an algorithm, right? A software program is a kind of a based on pseudo algorithm that you write. It's a pseudo code.
But program doesn't look for a pattern, whereas machine learning looks for a pattern and adjusts itself.
Absolutely, Anil. Right. So one thing that is coming out clearly is the patterns. That's what we would look at. But there is a little more to that one. Definitely, patterns is one thing that is playing a role. But what about patterns? That's what machine learning is all about. So if you remember the way that I mentioned during the previous sessions, essentially, so let's say you have some data and you have a set of code. So you write your code, you feed your data, and you get an output. That's what a software program does. All of us agree?
Yeah.
Right now, for me, a machine learning model, algorithm, whatever I call the terminology, I'm not too finicky about the language that I use. I can use model, algorithm synonymously, but I have a set of data. Then I know what is the output that I expect, and I feed the data that I have with me, and I know the model, what the expected output is, and the outcome of this machine learning problem is the model. The model comes. Here in the software program, you have data, you have a model, and you're getting the output. But you have your data, you know what is the output that you expect, you give these two things, and the machine learning algorithm will give you the model. What is the expected model that needs to be done? So for that model, you feed any amount of data, it gives the expected output. That's what the purpose of this model is all about. So the fundamental hypothesis essentially that we ran with is, we are not trying to generate a program. We are trying to generate a model where clearly know what is expected. In a software program, you don't know what is expected of. You are waiting for the output. Here, the output is the model. It's a slight change of the structure. And the definition that Mukesh used in the classes, I'm just reading out. I noted it down. So machine learning is a field of study that gives computers the ability to learn without explicitly programming. That without explicitly programming is you already have the output, you give that, and the model is the one that you are expecting out. That's what I refer by the machine learning concept here. And one thing Anil mentioned is patterns. So what patterns are we looking at? So why do we use machine learning for patterns?
What's the question, Ram?
Why do we need machine learning for patterns is what I'm saying. Patterns is what Anil mentioned, that is one of the important things that we try to learn. Absolutely, we use machine learning for patterns, but why machine learning is the question.
Because it can learn by itself, right?
Based on the data, it predicts the result in
Yeah.
the
Right. So this as Anil was talking about, sometimes the answer is straightforward, but we try to think that there is something deeper in the question itself. My question, I assume, at least from my sense, it was a straight simple question. What I was trying to essentially is when you have data at your hand, when the data is small, manageable enough, and you can observe through visual inspection, or when you can observe through just skimming through the things, you can identify some patterns in the given data. That is fine, but you need a kind of a statistical algorithms or machine learning algorithms at this particular one to find the machine learning is because majority of the times in the real world data we have these patterns very much hidden in lying inside the data. They're not pretty obvious for us, and as the volume of the data grows, it is difficult to unfathom all the different dimensions, different nuances, different patterns, trends, seasonality, cycles that exist in the data. It's difficult to find us. So difficult to find for us by normal methods. That's why we try and employ machine learning algorithms to unearth those things. Sometimes they are very subtle, and a normal analysis also cannot catch them. So we tend to resort to these machine learning algorithms. That's what machine learning is. Now, there are two types of machine learning or three types of machine learning that we touched upon. What are the different types of machine learning algorithms that we looked at?
Unsupervised and hybrid.
Yes, supervised, unsupervised. Hybrid is the term that he used. We'll touch upon hybrid, what hybrid means and where hybrid will come into picture. And we touched upon one more. First is supervised, second was unsupervised, and the third one is reinforcement learning. Right? So let's quickly spend one minute on each of these things. What is supervised learning? We'll touch in detail today, but based on what we discussed, what was the supervised learning concept?
So we have a data based on that pattern. It does it find out the corresponding patterns. It knows that already has been some pattern over there. Some based on that it it finds out the outcome of next pattern.
Yes. Anybody else?
It usually has one predefined target variable, and based on some independent variables, the target variable is expected to be predicted. And also,
Right, Prasad. You're right, Atanu. What you mentioned is right. There is a value that is out there, but as Prasad mentioned, there is a target variable which is already defined, which we call as a labeled variable. So the target variable essentially refers to what is the outcome you are looking at. If we looked at the first statement definition that I talked about, you have your data and you know what is the output you are looking at. And you have that output labeled. What is your required output that you want, that is labeled? You know what needs to be accomplished. You use the target variable which is labeled. Essentially you use that to supervise the modeling process. So for the model to come out, it banks on the target variable, and the target variable acts as a supervisor. That's why this whole thing is called as a supervised learning. So your whole model is essentially banking on the target variable. So everything is revolving around what is that is expected out of that particular, what is the outcome it is looking for, why a particular data or a record is giving this particular value, why is this connected. It try to identify the relationship between the supervised variable that is out there, the target variable, versus all the other data points that you are trying to use to predict the target variable. That's why it's called as a supervised. Now we get the concept of supervised learning. Anyone who's having some more doubts on that one? Anyone? Because this is very important. I know this is very basic. At the end of the day, this is important also. Why this is supervised learning is you have a target variable. The target variable is the one that defines how the output model is going to come out to have the required prediction. That's why it's called as a supervised learning. The target variable supervises the whole process that goes around in this process. That's why it's called supervised learning. There are two types of supervised learning. What are they? Folks, first class.
Regression and classification.
Perfect. I don't call regression, I'll call it prediction. Regression is one of the techniques, but at the end of the day, we use prediction and classification. Absolutely, that is right. So prediction, when do we use prediction? When do we use classification?
For numericals, we use prediction, and for nominal variables, we use classification.
Categorical variables, we use classification. Brilliant. Brilliant. Now coming to unsupervised learning. What is unsupervised learning?
There is no specific target variable, but the ML is expected to find some clusters or some similarities or correlation within the all.
Exactly. So in supervised learning, you have a target variable, you know what to expect, you know what are you looking for, aiming for, which is acting as a supervisor. So it's called supervised. But in this case, you don't have the data labeled at the end of the day. See, label does not mean it's like, okay, 1 is this value, 2 is this value. It is more about, you know that this is a predictable value, this is what needs to be predicted, this is what is the outcome that we are looking at. That's what the labeling means in this scenario. So we don't have anything of that sort. So when you look at a data set given to you, you don't know which variable is influencing which variable, what is all there, which is your dependent variable, which is your independent variable. You don't have that sense of understanding of the data. All that cluster and the lump is given to you. Based on that, you start forming your patterns, you start making your predictions, you start making your inferences. So that's why it's called as an unsupervised learning. There is no fixed approach to that particular one, right? That's unsupervised learning. Brilliant. And the third one that we touched upon is reinforcement learning. What is reinforcement learning? So this can be like you exactly don't know what are all your outcomes, but you know one particular outcome that is required for you. Whenever the model produces a required outcome, we start incentivizing that particular one. So let's take the small example of the kid. When your kid writes an exam, comes home, and next day the marks come, and he gets first mark in the classroom, in the class, in the exam. So what are you going to do? Congratulations, you wish him, you praise him, or you give him a small token of appreciation like a chocolate or a small toy or something, or you take him for a movie, you take him to the park. What goes into his mind?
It's a carrot and stick algorithm, right?
Yes, exactly. You're rewarding a particular behavior. Tomorrow he participates in a game, he comes back with a trophy, again you do that. And the next day, for example, on a different subject, when an exam happens, he is getting very less marks in that particular exam. What do? Then also you take him to park, then also you take him to a movie or buy him a toy. Then he does not distinguish the value of getting that first mark or standing out in a class versus getting less marks. So on the contrary, what do? You start giving him some lecture. You start giving him this instructions, then you start giving him a sermon saying that this is not you should do, this you should read, or you should spend more time on this subject. Then he understands, okay, this is not what is expected. And when he starts differentiating the patterns of where he is getting a reward versus where he is not getting, in a normal scenario, any student, any kid would tend to simulate or emulate the behaviors which are giving him more and more rewards. Reinforcement learning work exactly on the same concept mathematically. So whenever it gets an outcome which is desired, it rewards that particular prediction. And all those scenarios where those expected outcome is coming out, it identifies those things and cuddles them together and then identifies patterns between those things. That's how a reinforcement learning works. That's a very, very superficial way of understanding reinforcement learning, but at the end of the day, that is what is there. That's how it is done mathematically is a different problem for us to deal with. But the concept of reinforced learning is as much as that. Is that clear?
Yeah, that's fine.
Right. So now coming to the hybrid learning, because Prasad, you mentioned hybrid learning, and I know Mukesh also mentioned it somewhere in the video about hybrid learning. So hybrid learning is a mix of a supervised and unsupervised learning. Let's say, for example, you have a totally new problem that you don't have any handle on, you don't have a sense of. Then what do? You have given just a dump of data. You are a data scientist, a dump of data is given. So Atanu, this data is given to you. Just tell me what is coming out from this data. Then you don't know what is dependent, what the data is telling or anything. Then you start trying to explore that data and figure out some pattern, something. So what are we trying to do here? Unsupervised learning. Once you do an unsupervised learning, once you know some patterns, then you observe that, okay, this set of people are classified, and when these people are together, this is exhibiting this behavior, which means what is the behavior that is exhibited, you identify that as a dependent variable. And what are all the characteristics that are leading to that particular behavior, you identify them as an independent variables. Then you start building a model using independent variables to predict this dependent variable. And then you get into the accuracy levels of how much accuracy my predicting behavior is everything. So in the first phase, what you did is unsupervised learning. Based on the findings, patterns you come up, you create a target variable, you create feature variables or the independent variables, whichever you call, and then you start building a model around them, which is supervised learning. So a combination of you start with unsupervised and end up with supervised is nothing but your hybrid learning. Is the concept of hybrid learning clear?
Yeah.
Good. So just with these concepts, now get into some things that are covered in the classroom. I'll use the slides for that. But this is the content what we are going to cover. Introduction to machine learning, why it is important. I think we already beaten that thing to death. We understood that. Now the next one is machine learning, how it happens in mathematical space. Then what is supervised learning? We covered this piece already, but we'll come to that. Then we'll get into actually the concept of linear regression, what linear regression means and how it is. Okay.
Ram, Chaitanya here.
Yes, Chaitanya.
Yeah, is it possible to give one example, practical example?
A practical example for
this all supervised learning, unsupervised, and then
brilliant. We'll do. So there are
understand, because I
there are
still
examples
understood
coming
the full concepts of this.
There are examples coming up. Let's touch upon that. First, let me go there. Okay. So the next slide essentially is about that one only. So let's look at this slide and then go there. Okay. So introduction to machine learning. What does this? We already touched upon the ability to do the tasks coming from the underlying model, which is the result of the learning process. We touched upon that piece. The definition that Samuel gave about this one. Then the model is generated from huge volume of data. We understood, because we have simple data, small data, we can observe the patterns, maybe visually, maybe with a little bit of simple analysis, but as the volume of the data grows, we cannot identify that. Huge both in breadth and depth, reflecting the real world in which the processes are performed. So we look at that. Then what does the algorithms do? Machine learning algorithms, be it supervised, unsupervised, I'm not distinguishing here, but searching through the data to look for patterns, as Anil mentioned, in the form of trends, cycles, associations, then express these patterns as mathematical structures. This is the important piece. See, at the end of the day, any relationship, any pattern, anything that you are finding, intuitively human mind can understand, but you have to represent it and explain it to others. You need to put it literally, symbolically, somewhere, so that the others can comprehend. Your intuition has to translate. That is nothing but these mathematical structures. You say that there is a relation between two variables. How is that relation expressed? That's a mathematical equation, what we bank on. That can be a probability equation, probability representation, or that can be a polynomial equation, quadratic equation, or it can be an exponential, algorithmic, hi-fi, anything that can be there at the end of the day, but you has to have a mathematical representation for it. So that's what algorithms do. Now coming to the examples part that you talked about, is Atana, is that you asked for, or Chaitanya? Chaitanya, yeah, sorry. Yeah. So these are the simple examples, industry use cases that are out there, but we'll talk about these things. So the first example of simpler use cases, let's look at the simpler use cases first, then we'll go to the complex ones. Predict if a customer will default a loan. So let's say, for example, I'm a bank who gives out loans, right? So now I need to find out, somebody comes with an application for me. I need to figure out whether this person is going to be a defaulter or will pay loan on time. How do I decide? What is the simple measure that we use these days for that purpose? How does the credit card agencies operate?
Credit rating.
Credit score, whatever you call, that's the score, right? What does the credit score tell at the end of the day?
History about the transactions.
Yeah, but at the end of the day, credit score is just a number for me, right?
It's a credit worthiness, right? I mean,
Yes.
it's a number.
Yeah. So where is that coming from?
From a large data.
Yeah.
Okay, what kind of data?
It's a mathematical calculation of weightage given to each of the the credit defaults or
From your repayment history.
Yeah, repayment history. Good. I'm looking at
Target variable.
Target variable is whether you default or you pay on time. That's what I'm trying to predict, right?
Correct.
But that I'm deciding based on credit score. So let's say, for example, on an average, what is the maximum credit score one can get? 850, so somewhere around that, right? 850, 900 somewhere.
Yeah.
And
right.
a very good credit score can be somewhere around 800 plus. Excellent is what we call, or 700, 750 plus is called as a good score. And below that is average, fair, and everything. That's how the rating goes. So where the score rates, based on that, I'm doing a classification and I'm deciding on whether the loan or the credit has to be given or not. We'll decide. But to arrive at that score is a quantitative metric at the end of the day. So how am I arriving at this metric? That score of 600, 700, 800, how am I calculating that particular one?
So amount paid on time, amount
Yes.
defaulted.
Amount paid on time, amount defaulted. What else?
Number of loans you have.
Number of loans you have.
Number of credit cards you have.
Number of credit cards you have.
Income.
Your income. Enough. But are you getting what we are trying to do now?
We are converting this into a mathematical formula, right?
Exactly. And Prasad used one beautiful term there in between. Prasad, can you come back with that one? What you said?
I said it. Just trying to convert this into a mathematical formula, right?
Formula, but you used some important term there, which caught my attention, which is exactly what we'll do.
I forgot it, Ram. Maybe you can say that.
You said we are giving weights to each of these.
Yeah, exactly.
Form a mathematical equation. What are those weights that you are referring to?
It is a probability or the importance of that.
Exactly. Now you hit the nail. You are talking about the importance. Chetan, you are getting, let's say, for example, the variables that I take for issuing a loan or calculating the credit score essentially is, one is my income, my current income level. And second one is how many credit cards I have, how much loans I have, my past credit history when I have done. So let's say I am having a pretty good income. Is it a good predictor of my credit worthiness or not?
It's one of the predictor for sure, yes.
All right. But let's say, for example, I earn 5 lakhs every month, hypothetically. But just earning 5 lakhs makes me enough good enough for getting a good credit score? No.
Certainly.
Because I might be gambling, I might be losing money, I might be taking huge amount of loans with respect to my earning capacity, and I'm not repaying them. So 5 lakhs as is not good enough. But generally, we consider 5 lakhs is a pretty good factor. So the relativeness of that factor vis-a-vis the other factors also plays a role. Then let's say, for example, another guy who earns just 1 lakh, but has just 2 loans, which is of 50,000, which is of 70,000, two loans that are there. And he takes an EMI of monthly 5,000 for each kind of a thing. Then he starts repaying them on time without fail on 1st of every month. So should I trust the first guy? Should I trust the second guy? You obviously trust the second guy. Though his learning capacity is less, he is more prompt. So there are other factors which are weighing more important. Chaitanya, making sense?
Yeah.
So now, at the end of the day, I will create a mathematical function. My function is credit score is equal to f of means is a function of earning capacity, repayment capacity, promptness in repayment, number of credit cards, number of loans, number of times defaulted in terms of EMIs, number of loans that have gone totally bankrupt, not paid at all. We'll take all these factors into account, and then I'll create that mathematical equation. Now, each of these factors, which I identified as my independent variables, which are within a function of all the variables that I listed, all these variables will become my independent variables, and each of them come with its own weight. What does this weight represent at the end of the day? What are the weights represent? It is the relationship between that particular variable and that dependent variable, which is my credit score. how much this particular variable has a bearing on my credit score, and how much this variable is important relative to other variables also. Two dimensions it will provide me. One, it is a relationship between one, and the other one is vis-a-vis the other variables. But let me say, I'll put another question here. This is very subtle at this point, but this will have a huge role for you to consider in the long run, because this plays one of the important dimensions. Let's say my earning capacity I'm talking of. Let's say I have two earnings at the end of the day. One is my salary. Second one is my non-salary income. I'm breaking my income into two parts, right? I'm using two variables at the end of the day. Does that have a bearing on my particular credit score?
Yes, of course. Should.
In what way?
The weights could be different. For the salaried income, weightage should be higher. The non-salaried weightage should be a little lower. So it should have a weight.
But at the end of the day, it's all my income only at the end of the day. All the income is, that is what I look for.
One may be stable income, one may be non-stable.
Yes.
income.
Yes.
Yeah, exactly. Right.
Right. Okay. So now let's say, for example, look at a different scenario where one variable is also a function of other variable. Okay. My salaried income is, I have a salaried income, then I have my bonus. My bonus is a function of number of extra hours that I do and everything. You're getting the connection. Salary is the regular salary I get, but my bonus is the function of the extra hours I spend in the office only.
It's a coefficient of something.
Yes. So at the end of the day, my total salary is equal to sum of my fixed salary plus my additional salary.
Correct. Right.
Right. So this is the subset of the number of hours that I'm working on in the office only. So one can be expressed as a function of the other.
Correct.
So those two variables do not explicitly tell additional information where one variable is not telling you. At the end of the day, both the previous example also, my intent essentially was to drive home the point is salary at the end of the day is a salary. Though you break it, one variable can be represented as a function of the other variable. For example, in the previous case it was not, but in this case, yes, it is. The function of one variable can be represented as other function. You don't need to have two variables, because one variable itself is sufficient enough to explain it. Or you combine both variables and create one variable as a total salary. Just say that how much is your total salary. Is this concept making sense?
Ram Chaitanya here. Sorry,
Chaitanya.
this basically there means in the video what I seen that he has put that force and he's saying that okay, human brain immediately understand that what exactly and immediately find out, and when we say the program and if we add one more 4 there, then program is not able to understand.
Right.
Exactly. Right. This concept of coming, this machine learning concept comes. So in this example which you have given, where everything is logical, means it can be placed in the program. So why machine learning is required here? And I'm not able to understand that where exactly what he's saying that adding 4, how this model is understanding that yes, this is a possible, or in this example that
right.
Logical steps where program can be set that these are the things, then yes, the credit score is this and he is eligible. Excellent question,
Chaitanya. So if I had to re-articulate your question, that I understand and also others follow. I'm assuming others followed, but this is for my clarification. I'm re-articulating the question. In the example that is given in the video, where a character 4 written in one way and other person writes 4 in a different way, it's difficult to identify whether it is 4 or not. So you need a machine learning algorithm, makes sense there.
Yeah.
But while predicting a defaulter for a particular loan, should I go ahead with giving a loan or not? Or if somebody has already taken a loan, can I predict whether that guy is going to default or not? Okay, in either of the scenario, why do we need a model, right? My point is, think from a bank perspective now. Let's say you are a bank manager. How many customers on average a bank will have? Take State Bank of India, which is the largest bank. How many customers State Bank of India has?
More than lakhs or millions?
Maybe millions for sure.
Millions is what I would look at least 70 lakhs, 80 lakhs, 1 crore, 1.5 crore customers. Somewhere around that is the margin that we look at. At least 70, 80 lakhs is what I'm estimating, roughly. All forms of customers, when I say customers, it could be someone who just opens a basic account, someone who has come for a loan, someone who has a credit card, someone who has a agriculture loan, someone who has a car loan, someone who has something else, house loan. Take any form that is there. Some people may not have a bank account, but they have a bank loan. Some people have both. Some people may have only one. Take all forms possible. I am taking their scenario. At bare minimum, look at least 15-20 lakh customers that are there, which is 2 million customers the State Bank has. Now, when you have to give a loan, how many parameters that we have identified in a little while back for calculating the credit score? 7, 8 variables.
Yes.
Right? Your salary, your tenure in the organization, how long you have been working, whether you have a fixed property. I'm adding more now compared to what we discussed. Whether you have a fixed property, whether you have a loan on your fixed property, whether you have taken any loans or you have any mortgages, or you don't have any mortgages, whether you have taken loans in the past, how many loans you have cleared of them, how many loans are currently in vogue, and what is your repayment schedules for each of these loans, how many of them you have defaulted, how many of them you are paying on time, kind of a thing. Now you take all these parameters. Let's say tomorrow you are the loan disbursing approval officer who is sitting on the counter, and I come to you for sake of loan. Right? Chaitanya, getting it?
Yes. Yeah.
So in that scenario, so how much time you will need to assess my candidature or my application and decide that whether I fit in to be given a loan versus I don't fit in to be given a loan? How do you do?
It will be traditional way. It will time consuming.
How much?
Traditional approach maybe 1 day or 2 days.
1 day, 2 day for one person.
Yeah.
You need to sit, do the background homework and everything. What about people like me coming every day? Thousands of people come knocking the bank doors for sake of loans every day. How many Chaitanyas need to be there to disburse all the loans that are going? You're getting the complexity of the volume of the data, right? Now I'm talking of the volume of the data, problem 1.
Yeah.
Now look at phase 2 of the problem. This is the complexity of the challenge that is there. I come to you, I have paid 3 loans, which are almost 15 lakhs each. I have paid 3 loans on time, very correctly and everything, but I have taken a small loan for 50,000 something, which I have not repaid on time. There is default that has happened for whatever reason, and I had paid penalties and everything, and finally I cleared that loan 6 months later, paying penalty and everything, because of which I took a beating on my credit score, and there is a default this thing listed for that particular loan. I paid 15 lakhs clearly, but there is a default tag that is attached to me because of that 50,000 which I have not paid. The reason I have not paid is I went to abroad, because of which I didn't have any way to transact with my bank for whatever reasons, and I didn't bother put whichever way. Then I came back 6 months later, and then I paid my loan. But still I have this particular one. So if I come to loan for that one, judgmentally, will you give me loan or not? If I explain you this scenario.
Yeah, by checking the conditions, and if it is okay, then the loan will be applied.
But is there a fixed way to figure out, okay, apply all these criteria, you can be given loan versus you cannot be given a loan? Is it a rule-based thing, like the program that we talked about earlier, software program? Right?
It's relative. It's a relative.
It's a relative. What is that relative at the end of the day is boiling down to? What is relative? What does relative mean?
Is assessed based on the case to case, and then
Case to case. What is that case we are referring to? Good point. What is that case and relative all we are referring to? We are referring to one single thing that we learned in last 2-3 sessions.
Probability.
Exactly. That is probability.
Mm-hmm.
You are measuring the probability. The moment you go into the probability, there is no 100% yes or no fixed scenarios on either side to go with. So then your human mind can do very intuitively to do that, but you cannot do every case and do it without fault. Then you need to bank on something larger, something more efficient, something more systematic, something more rigorous and more capable to do the decision on behalf of you. That's why when the data comes in, they say that we revert back in 3 days to fill up your application. What do you do in those 3 days? You feed all your data related to this. Then your IDs we take. I take your PAN card, I take your loan details and everything what you have earlier based on the application data that you have. Then I feed all that data to my model. My model will give you a probabilistic score of 67%. Then as a bank, I would have drawn a line somewhere at 65%, 67%, 70%, anything above 70%, it is safe to give a loan. If I am falling above that line, I would be given a loan. If I am falling below that line, I will not be given a loan. You're understanding?
Yeah.
So that's where the model will come into picture. So when you have such a huge volume of data, sometimes similar scenarios, let's say you flip some other cases, some guys have paid all simple loans, one complex loan he could not pay. Then what do? You trust on his repaying ability based on simple loans, or you have a doubt because he could not pay one bigger loan? How do you tweak it? Then you need to calculate the probability again. That calculation of probabilities is what the model does at the back end for each of the scenario that comes in. That's where the machine learning will come into play. Then it classifies whether you will be a defaulter, whether versus you will be a prompt payer. That's why a model is required. Does that help?
Yes. Yeah.
Does that answer the question?
Yes.
Yep. Great. No, I know we took one example and we looked at very granular because the idea is for you to comprehend what is going on. We spend good amount of time there, but let's look at other examples. What is the probability that an employee will quit his job? This is a very standard problem, right? If you are all in a managerial roles, one thing that is there on our scorecards at the end of the day is attrition. We are bound to be hit by attrition. So my scorecard, my bonus, my performance, and my evaluation at the end of the day is also decided by how many members in my team have attrited. So how do I know whether this person is going to attrite or not? While I am bothered about just 5 people, 10 people, or 50 people in my team, the whole organization looks about 10,000 people, 20,000 people. The organization has to come up with some kind of a model to understand why a particular person is likely to leave. Is he likely to leave? What are my red zones? What are my flags? How do I identify that this person is likely to leave? Those are the things that I need to measure. So I will come up with a model. So then I will check his past employment history. I will check his signals, how many increments he got, how many good ratings he got, how many bad ratings he got, why he has given that ratings. Then what is the increments that he got? I'll take every factor that is out there, and then I come up with a attrition score, likelihood to attrition score kind of a thing. I'll calculate that. That's what my probability is. Then based on that probability, I'll tell this guy is likely to attrite. Then I'll give a time factor also, how much it goes. The customer churn, like you look at employees in an organization, customers for a retail organization. Let's say I regularly go to Big Bazaar. I have a relationship with Big Bazaar, but suddenly I change from Big Bazaar and I start going to Spar, or I start going to Metro, a different hypermarket that is out there. So then why will I leave that company? I leave this from this retail store and go to the other retail store. What factors influence? Everything has its own things. These are simple, straightforward equations at the end of the day. Predicted sales for the product for this year. Simple ones. But now you go to the complex use cases that are there. Detect the audience sentiment for a new movie. Is this simple or difficult? What do people think?
It is complicated because you need to root through the entire comments and find out the sentiment, right? Sometimes it's complex. It may not be a straightforward comment.
Complex in what sense? How are you capturing the sentiment?
First of all, collecting the data is complex, and there are so many platforms you need to go in.
Right. So the data is very dispersed.
Yeah,
It's not in single source. Point well taken. Let's say you collect all the data and put it in one form. But how are you getting your data there?
It's unstructured, right? It's in the form of text or voice or.
Yes, sometimes people provide a rating. Sometimes as soon as a movie releases, I see tomorrow 3.5 out of 5, 2.5 out of 5, 1 out of 5. We see the ratings, but that's an aggregated score. But there are comments also. How do I connect these comments versus those actual ratings that these people have given for that particular one? All the score I see is an average score, but we have seen the challenges with averages in the past. They are very much influenced by outliers.
Yeah. Yep.
So how do I calculate that? Then how do I decide my then there is a textual data that is out there. Then somebody just put a smiley. How do I interpret that smiley at the end of the day? So that's where the challenges come with one. That's why it's a complex use case. Then the second one, Chaitanya, as you mentioned, the character recognition. So this is basically the OCR problem, optical character recognition. So a human handwriting, you write EA in certain format, I write in certain format, the strokes are different, the length of the characters are different and everything. So identifying them and using the strokes patterns in writing a particular character and everything so different. Still, am I able to make it correctly, identify that character correctly? Is character recognition. So it is definitely a interesting problem to look at. It's not as simple as just doing a default loan. That's even you have at least all the data is one type, you know what to do. Everything is pretty crystal clear for you in a structured format. But these are not like that, because this is at the end of the day character recognition. You are getting into an optical recognition. It's a pixels. You have to deal at a pixel level and start doing it. So the problems are different there. Then too complex, too dynamic. Weather forecasting. We all know. Every day I see on my phone rain prediction 80%, and I don't see rain on that day at all. And when I see 20%, it might be raining in the next half an hour. So how do we forecast? What are the challenges that the meteorology department goes through in this scenario? So what are the factors that will influence? Let's just touch base on one thing. Why it's challenging, weather forecasting?
It's continuously changing. Variables are more
Right.
variables gets added.
Right. So the dynamic nature of the factors. But what is causing the dynamic nature? See, is predicting weather in India versus predicting weather in US, which is easier? Did we touch upon this one? I remember touching this factor at some point.
Specifically versus India, US, I don't think we discussed, but we discussed.
No, we have not discussed that.
All right.
No, I
See,
think they're not discussed.
in US, the climate is far more predictable. When I say US, at least in Western countries, the climate is far more predictable. When something happens, it's more likely to happen. At least having spent a couple of years in US, I have seen that when rain is expected today afternoon after 3:30, definitely the rain comes after 3:30. I have seen that, which is very unlikely in India. The reason also being the zone that India is in, particularly the Tropic of Cancer, Tropic of Capricorn, and everything, the region that we are in, the kind of a monsoons with sea on both sides that is out there for us, it is really, really difficult, because you predict on one side and the monsoon comes from the other side also, and when they have that mutual interaction effects, you don't know what is going to happen. Sometimes it suddenly becomes a very low pressure area, sometimes it becomes high pressure, then everything evens out. So that predictions becomes a little tougher there. So you have to take into so many factors. What is the pressure at a given point? How much it is changing per hour, kind of a thing. Then how is the temperature playing a role? Then the cloud behavior. So many things will come into play. That's why this is such a complex and dynamic scenario. Then recommendation systems. So you all use Amazon, Netflix, Prime.
Yes.
Yep. Yeah.
You watch 4 movies. Do you see the immediately automatically the next day or next half an hour some line appearing saying that you may also like? It gives you a set of movies.
Yeah, even in YouTube, right? YouTube or Netflix. Yeah.
Yes, anywhere. So basically you choose something, it gives you a list of you may also like these things. Why? How does it guess that these are the things that you might like? More often than not, those could be the genres that you would like, or the movies that you might end up watching. How will it figure out? How is it able to recommend?
A recommendation based on other people have done similar things.
Yes, recommendation based on other people. There is one dimension is the people. Any other dimensions to look at?
Genre of a movie.
Basically, it's the content.
Yeah, content.
Content. So one dimension is content, the other dimension is people. So based on that, it starts churning out the whole set of information that sits out there, and there are so many variations between people. Some people likes these movies but does not like that. Then based on your behavior, what you have liked, what you have not liked, what you have watched but not rated, but what you have watched and rated tells you your intensity, your passion, and your sense of relationship with that particular thing. Based on that, it comes up with a model, essentially. So that's why the recommendation systems is a little complex system to provide those recommendations. Particularly as the data base is huge, this becomes even more complex. Then genetic code mapping. We don't even need to talk about this, right? How many chromosomes we have?
23.
Yes. The pairs of chromosomes, 23 pairs of chromosomes, essentially. So given that the permutations and combinations that are happening is phenomenally complex. So you have to predict something. The permutations and combinations are totally difficult. There are random examples, complex use cases of machine learning, how it goes in terms of predictions. Now coming to the actual machine learning, how does that work? The data, this thing appears. So we all have been talking in the air about so many variables. In the previous example of bank, we talked about n number of variables. Your dependent variable is primarily whether you're a defaulter or not a defaulter, and your independent variables are your salary, number of loans, number of credit cards, xyz, abc, everything that is out there. So in total, let's see, you have identified 15 independent variables and one dependent variable. How many variables we have? 16. Now what do you mean by you have 16 variables? When you look at in an excel sheet, it is 16 columns multiplied by number of observations and number of people you have data on. That's what your data set is. But you have to translate this into your mathematical space. How does that look like? So one variable essentially we call as one dimension. So on one variable, you can understand any kind of a thing. Let's say you have only one axis as a scale. On a scale, you say 0, you say 1, you say 2, you say 3, or -1, -2, -3. You will understand that scale because it is all on one line. But the moment I put in one more dimension on that particular one, let's take a very simple example. Forget all the complex examples at the end of the day. Let's talk of a classroom. Take our class only. We have 10 people in this session who are attending this session. Let's take the height and weight of each of the person. As long as I'm talking about height only, it's just one dimension I'm looking at, only one factor, one variable I'm looking at. Then how do I plot? I draw a line and I arrange them, all the people in the ascending order, descending order, whatever you call their respective points on the scale, and plotting them easy. But the moment I take weight of each of these people into other people also, then what scenarios exist? I'm getting into it's no more a line. What am I changing into? You would have watched the videos, the mathematics
Maybe
videos.
a plane, in fact.
Yes, you are getting into a plane at the end of the day. So you have a height on one axis and weight on the other axis. The moment you do that, then you start pointing out each of these people on a plane. It's no more on a line anymore. You're plotting them on a plane. So then there are different nuances that will come into play. There would be people who are having higher weight but low weight. More height but less weight, or more weight and more height, or less weight and more height. All different scenarios that are possible, you will start getting into them. So then when you plot and visually start looking at all these people, then you can say, okay, there is a cluster of people in this particular class who are having good amount of, they're really high, really tall, but they don't have that much weight. They're really lean. So that's what one interpretation that can come out from this particular one. Or it could be like, these people are really robust, They are good, really tall, and they have good amount of weight also. Could be other information, but that you start looking at when you see the scatter plot. So the moment you start plotting all the people or all the observations in a plane which has two axes, a plane will have two axes, and plot them, then you will start observing them in a plane like here. So now you come to the example that is coming on the screen. The example that is taken is there is one data set which has 7 columns, but out of these 7 columns, they have plotted only 3 variables. The reason Mukesh told essentially is which is right is our human mind can interpret only 3 dimensions to the extent possible, 3 axes. The 4th dimension for us is always still difficult to comprehend. Whereas visually, when you start plotting, you can start looking at 4th dimension or 5th dimension. To extent of 5th dimension, you can look at. So your x-axis is 1 dimension, y-axis is a 2nd dimension, z-axis is 3rd dimension. What is the 4th dimension here?
The colors.
Colors. 5th dimension also Mukesh talked about. What could be the 5th dimension?
It could be the shape of the dot, right?
Shape of the dot. Yes, he talked about the shape of the ray. So visually you can look up to 5, and maybe if you think in a different way of looking at the things, you may bring in 6th dimension, but that's all. We cannot go beyond that, by which time you're already lost, because just there are 10, 15 observations here, we are able to at least think through. Imagine when your data has 1 million records. In a big data environment, that is bare minimum that you look at. So it's even plotting them, observing all of those things will become very tricky. So that way, 2 dimensions and 3 dimensions is maximum you can think about, and we cannot think beyond that. That's the logical idea behind that particular one. So now everything that is out there is represented by different characteristics. If you take just this point has, at least in this scenario, has 3 characteristics being represented. It is whether he has what is his age, what is his BP level, what are his sugar levels, and whether he is heart healthy or not healthy. Potential ailment is there. That's what this data point says. So every data point gives us that interpretation. So every data point you can start representing in a mathematical space. This is also called as feature space or mathematical space, whichever you call. So the reason you need to understand this concept is, as we move from supervised learning, and within supervised learning you start doing linear regression, then simple linear regression versus multiple linear regression, then you go to classifiers, it becomes important. See, for example, in this one, at this point, if I have to draw a line that separates people who have potential heart ailments versus who are heart healthy, where should I draw the line?
It's a plane between the greens and reds. Yeah.
So if I have to really draw the exact line for this one, shouldn't this be like this?
Yeah.
Right? But is this a logical, rational, reasonable scenario to classify?
No.
Very unlikely. So how do I do that then? A simple, better way could be, is this a little easier for us to do?
Yeah.
But what is this leading to?
Some errors, right? Some errors
Yes.
both sides. Yeah.
Here there is an error. This one is an error. This one is an error. So, but do you think the previous one is a better option or this one is a better option?
This is a better option. The previous one is absolutely unpredictable.
Why?
This one you can convert into a mathematical equation.
Yes.
Sure.
This one you can convert into a mathematical equation. Whereas the previous one, while physically you can draw and do that, there is no easier way of, maybe you can come up with some equation, very, very complex equation. By the time you implement it, do it, it is not, it's mathematically feasible, but realistically not feasible. That's why you look at this thing. So what does this tell me? The moment I convert my problem mathematically, it is bound to throw some kind of a error. So we need to live with that error. How much that error we need to live with is something that we talked about in the previous sessions when we did hypothesis tests. What is that called? The confidence level.
Yeah. Type 1, type 2 errors.
Type 1, type 2 errors. So I classify this one as a potential ailment. All the things above this line are potential ailments. All the things below this line are heart health is what I classify. So this is a wrong classification. These two are wrong classifications in total. So am I okay to live with these 2-3 wrong classifications? So what are the implications of that one? So that I need to have some amount of business knowledge and then drive out of how much I can live with versus how much I cannot live with. That's where this concept of mathematical representation helps you visualize your complex real world problems into a representable space, and at the same time also identify what kind of a mathematical equations will make sense in this given scenario. Is this making sense? Why we need to construe the things in the mathematical space?
Yeah.
Yes.
Good. Right. So let's move on. So when you're looking at 2 dimensions, we saw a line dividing. When we look at 3 dimensions, we start getting into a plane. So the equations are different. When it is just 2 variables, when it is just y equal to mx plus c kind of a thing, it's a line. But when I say y is equal to m1 x1 plus m2 x2 plus c, what happened? It becomes 2 points. Then it becomes a more complex scenario. Then it becomes a plane. And when I say m1 x1 plus m2 x2 plus m3 x3 plus c, it turns into a hyperplane, which you cannot even visualize, because at least a plane I can represent this way. But a hyperplane I don't even, because I need to think about another dimension to see how it plays out into the things. Visualizing is difficult, but mathematically you can make sense. That's why that mathematical equation plays such an important role. Right. So a few points about the same thing. What are we discussing? A model represents real world process that generated different data points. It could be a complex plane or a hyperplane, anything. Then multiple planes can do the job, each representing an alternate hypothesis. So this plane is a classifier essentially. This generally is used during the scenario of a classifier. So classifying them into 2 groups. The learning algorithm selects that hypothesis which minimizes errors and tests the data. This concept of minimizing the errors is what we will focus on regression at the end of the day. In across all the things, we want to minimize the errors, whichever model you depend on. But when we come to regression, minimizing the errors is one of the critical pieces that we would look at. Any questions so far? Okay, I am moving on, assuming that there are no questions. So we touched upon supervised, unsupervised learning already. So it is put across again in a different way. Supervised learning, we have a clearly defined x and y's. For simplicity's sake, x is your independent variables and y is a dependent variable. But more importantly, we predict a continuous response variable or a categorical response variable in supervised learning. So it is more about prediction that happens. So that prediction can be a continuous variable, which is through regression, or you do a classification using it when it is a categorical variable. That's what we do in supervised learning. In unsupervised learning, as we already talked about, it is unlabeled data, emerging patterns based on similarity identified. Clustering is more about similarities and patterns. Association rules, essentially if somebody buys this, would that guy also buy something else? Or there are different types of rule based algorithms that come up, which are called as association rules. So that's unsupervised learning. Now supervised learning, what is this telling me? It's essentially the points that we discussed. I'm just reiterating. It's a class of machine learning that works on externally supplied instances in the form of predictor attributes and associated target values. So there is a y variable, which is a target or dependent, and there are predictor attributes, which are just, it's a nomenclature, nothing more there. You have x variable and you have y variable, which is independent and which is dependent. The model thus generated is used to make predictions. Examples is building models to predict the resale value of car based its mileage, color, hour. So if you want to buy a second-hand car, how do you go about? What are the attributes you will look for? And then finally, your dependent variable could be whether you buy the car versus you don't buy the car. Could be an example. So this is the same content touched upon again. So let me leave this. Okay. So now coming to the machine learning steps, this is something important for us to look at. So whenever you have to do a machine learning problem, take any problem, what is the first thing that we need to do? You might already be reading on the screen unless you are sleepy.
Identify the data required.
Okay.
I would say define the problem first of all.
Yes, exactly. So define the problem. What is that the problem that you are trying to solve? Let's say, for example, you are a consultant who is doing some data science problem, essentially. So you have to do that. The first thing that you say is, okay, I'll build a linear regression model for this, or I do a classification problem, or I do a reinforcement learning. No. As Prasad mentioned, the first thing that we need to understand is what exactly is the problem. Define the problem. Once we define the problem, what is the next step that we need to do?
Then I think identify the data required.
What data that I need to solve this problem? Do I have all the relevant data? Guys, this looks very simple. Identify the data required. This is one of the very, very, very important steps to look at, because more often than not, we end up playing with the data that we have than looking at whether this data is making sense for me to solve the problem that is on my hand, versus am I having more data than required, versus am I missing any data that is mandatory to solve this problem. Unless we can completely get a sense or an understanding of that kind of a business sense of understanding the problem and understanding the right data for that problem, you are not going to make any progress with any of the remaining steps. That's why while this step looks so simple, so naive to state even more simplistically, it's one of the very, very critical problems. Are we clear with that part?
Yeah, yes, sir. In normal business intelligence use cases, if you say the data identification is, I would say, 80% of the
Yes.
solution.
Thanks, Prasad. That was my next question. When you start solving the problems, do you know how much time we spend essentially as a data scientist? How much time you will spend up in each of these steps?
80% on data, training, acquiring data, and 20% maybe on building.
Defining the problem, identifying the data, and pre-processing the data, and creating a training data set will take 80 to 85% of your time till this point. Selecting the appropriate algorithm could be 5% of your time. Then train and building a right model, which can take days together sometimes to build the model and prepare the model that comes. Then, and the effort is less there, but running time is more, but the effort is less. Then evaluate with the test data. So this whole process will take essentially just 10% of your time. The remaining whole process will take 90% of your time, 85 to 90% of your time. So data science is a pretty fancy area to look at. By the time you start doing your data cleaning, pre-processing, and understanding and creating a data, that's why in our organization, I'm talking of my organization right now, we create a database called as MRD. Do you know what MRD means? Just any guesses? It's called model ready data.
Okay.
There is a team that works on creating a model ready data.
That's typically we call data engineering team, right?
Data engineering team. So there is a database team, data engineering team, then platforms team. All these people will together identify information coming from different sources, put all that data into one place. Then we apply algorithms and everything on that data to curate that data, ensure that the data is in a right form. Then whatever the technology, whatever the applications of statistical applications need to be done so that the data is ready to be applied into the model. We won't go and do the pre-processing and everything. That data is ready to just pull into the model and use as it is. Because if they has to do a normalization, they have to do a standardization or scaling, anything that needs to be done, the data would have been ready. And details of how the variable, what treatment has been done to particular variable is already provided. We just use that database, pull that information that we need, and just we run the models. Despite that, we take so much amount of time till this step. Because the problem is ever changing, and you always have new data coming into play, and you need to merge that new data with your already existing MRD data. That synchronization takes good amount of time. That's why this process is such an important step in the process. Right? That's about identification of the data. What is pre-processing?
What database is used for the MRD? Just curious.
We use Oracle, Hadoop. The data sits in different platforms. There is a Greenplum, Oracle, Hadoop environments. Data sits in different platforms depending on different needs.
Like XML files and like a regular Oracle database?
Yeah, right. That is right.
Ram, one question. So who decides the data architecture? It is decided by the data science team or by the data engineering themselves?
It's a mix of both. There is a data science team that works together with data architecture. They have regular conversations as to whenever a new data comes in, what is the right way to transform that data? How do you keep it ready? What is the end requirement with that particular data? And then they do the transformations and make it MRD.
Okay, makes sense.
Right? Okay. So the next one is pre-processing. What do you mean by pre-processing?
Clean up the data for later.
What cleaning are we referring to?
Anything, putting a default value.
Removing some outliers, and some data may not be making sense. Remove them.
Outliers is one.
Update.
Missing values is 2. Anything else?
Formatting the data, like a date format and number format.
Okay. Date format and things is 2. 3. There is something more important. If you start looking from your data problems, you will start guessing this. You'll see these challenges coming in. The biggest problem that we generally see with the data is the scale. You talk of money that you spend in for your campaigns, advertisements, for example, take any example. I'm just using money as an example there. You talk in millions and millions of dollars, millions and millions of rupees. Isn't it the case?
Yes.
And when you talk of your returns, what is the scale that you talk about? How much return have you got? What is ROI? 5%, 6.7%, 8%.
Yeah.
These are actually fractional values. Then you take some other data, which could be age of a customer or age of anything that is related to. You talk in values which are in tens. And then you qualify that customer as a defaulter, non-defaulter kind of a variable, which is categorical in nature again. You have all this data in different types. And when you pull all these into the model, what does the model do at the end of the day? It takes the values on its face value and then starts calculating the variations. Let's say your ROI has gone from 5% to 6%, and your money that you are spending has gone from 5 millions to 10 millions. For 1%, 1.1 is the variation that you are seeing on one end, and 1 million is the variation on the other end. Do you think that correlates in terms of the scale of the values? It won't. Mathematically, it creates a lot of challenges, particularly when you do a correlation. Simple example. What is the correlation formula that we look at? Remember the correlation that we talked about? Sigma xi minus x bar, sigma is equal to 1 to n xi minus x bar into sigma y minus yi, or yi minus y bar divided by square root of
the variances, I mean, both of them. Right?
Both the variances essentially.
Under variances.
We got the correlation formula, right? So when you do that, imagine because of your multiplying 1 in millions range and 1 in decimals range, that multiplication, that correlations throws tantrums at the end of the day. That's why basically what we do is normalization of the data. What does the normalization do?
Brings, I think, all the variables into one level, right?
One level. What is that level? Zero mean and unit standard deviation. You remember that?
Yeah, unit standard deviation.
That's the Z distribution. What we so call the Z distribution is nothing but zero mean and unit standard deviation.
Yeah.
That's what it essentially does. That's what your distribution curve essentially is. That's what primarily you do in your pre-processing. You have to pre-process your whole data in that format. So you need to do whatever that is required so that the data is MRD at the end of the day. That's what the purpose of the pre-process. Now, the next step is training and test data set. I think we discussed this one also in the past.
One question, Ram, I think these concepts will be coming in future videos or some part of it, how to pre-process that, because some of the things which you explained are pretty interesting, but I haven't seen them in any of the videos. Actually.
These videos we don't have. So the upcoming sessions when we handle with the data, see for this week's session, I'm not even getting anywhere into Python. Finally, we'll take one example and we see how a regression coefficients are calculated. That's where we'll end today. Okay. But my idea is now today to explain what is a regression concept per se, what happens in the regression, what we're trying to achieve through the regression model, what does the regression line looks like, and how correlation and regression are important from each other standpoint. Then finally, take a sample small data set and calculate the regression coefficients manually. That's where we will end today. But when you actually start processing your data using Python, we'll do all these pre-processing steps. We'll talk of why pre-processing is required, what kind of pre-processing we do, and how that plays a role. We'll talk all about those things in subsequent.
Okay, makes sense. Makes sense.
Yeah. This is where I'm focusing right now at the conceptual stage as of now. The next step is training and testing. This is an important concept to keep in mind. Let's say, for example, we talked about this problem earlier. The data that we have currently is ever growing. You build a model using all the data that you have today. Would that explain everything that needs to be done? Maybe yes. But once I build my model and say that this is what I'm predicting with so much accuracy, tomorrow when a new data comes, will my model can efficiently and successfully predict the new data behavior? Now talk that through an example. Right now I have a bank customers of 10 lakhs loan applications. With all these applications, I build a model essentially and say that with an accuracy of 90%, 95%, I can say that whether an upcoming customer can be a defaulter or a prompt payer of the loans. I build that model. When the new data comes in, how much my model can successfully predict that? My 90% is based on what? The confidence level that I'm saying 90% is based on what? You're understanding my question?
Can you repeat once again, Ram? Sorry.
So let's say, for example, I have 10 lakhs customers who have taken a loan from my bank. Based on all 10 lakhs customers, I am building a model to predict if I give some data, whether this person who is coming new could be a defaulter or not, with a 90% accuracy level. Okay. So I build that model and everything is good. When I get my new data, something external outside of this 10 lakhs base that I have, some new customers come in, and now I need to verify whether these people who came for a loan would likely be a defaulter or would likely be a prompt payer. What could be my confidence level?
90 is what we decided, right?
90 is not what we decided. 90 is what we agreed upon based on what data?
Test data.
There is no test data that we have thought about so far. It's all the data 10 lakh customers you have used for building the model. So then you have not tested your model. You built a model. You're remembering it.
Got it. Okay.
And you are directly putting that into the production. And when your new data comes in, there is no way to verify because your model has not seen that data. You're understanding? You used all the data that you have to build the model, which is good because you took every possible scenario that would have happened. You have taken that into account based on your existing customer base. But when a new scenario comes into play, you don't know whether that scenario has already been tested in your model or not.
This could be a chance case or a fluke, right? I mean, so that's what
fluke also, essentially. So to avoid those kind of unforeseen situations where your model is likely to fail, what we adopt a scenario called as a test and training scenarios. You split whatever the data that you have at your disposal. So this is a standard a Bible instruction kind of a thing. You remember the 10 commandments of Moses. Whatever, you don't need to remember what 10 commandments are. The concept of 10 commandments in Moses, this is one of those things. If we have discussed about identifying the right data, pre-processing data as they are important, this could be the third of the 10 commandments of Moses for data science. You have to remember that you split your data into train and test data. What is the purpose? Because you have to build your model on certain amount of data and test that model what you have built on this test data. The training data is used for building the model. The test data is to test your model. You're following? Because how accurate or how likely your model is going to test the stand of time, test the stand of unforeseen scenarios that are likely to come up. That's why your model should never be exposed to the test data till the last minute unless till the time you're going to test it. Only when you know that your model is throwing up this much accuracy, this is my accuracy levels, this is my confidence level, this is what I am predicting and everything, you're good, you're conceptually have a good understanding of what your model is doing and you are satisfied with it. Till that point, don't even bring your test data close to your model anywhere. It should not whiff the test data at all. Only at the testing time that data should come into play. We'll see why that test data is important in a later point. But the test data creation is a mandatory thing. Then the next question that comes between is because you don't get any new test data. All the data you will get subsequently is the live data, your production environment. You cannot get that. So you have to create your training and test data sets both from the available data set. So there are different norms people follow depending on how much your data size is. You have 10,000, 20,000, 30,000, 50,000, 1 lakh, 10 lakhs rows, whichever way you are operating with. You have much higher data sets. You can go into 80-20. Or slightly smaller, 3,000, 5,000, 10,000. That's what your majority of the academic problems that we solve will try and look at 7,000, 5,000, sometimes even 700, 500 kind of a thing. Then you would look at a 70-30 split. So when you feel confident that even 20% of your data amounts to a significant amount of data that can represent all random possible scenarios and everything, you go with a 20%. Otherwise, you stick to 30%. You can range anywhere between 70-30 split, 70 for training and 30 for test, to 80-20 where 80 is for training and 20 for test. Depends on your choice. There is no fixed approach. It depends on your choice, your logical judgment. You can decide on the split of training and test. Is this concept making sense?
Yes.
Good. Once you create your train and test data, then you decide the appropriate algorithm. This algorithm can be either a linear regression, logistic regression, a naive-Bayes classifier, KNN classifier. You do a boosting, XG boosting, bagging. You can apply any of the techniques that are out there that suits to your problem that you're trying to solve based on whether it is a prediction or classification, whatever it is. And then you train your model, you get the outcome of the model, and then evaluate with the test data. These are the steps that are involved in the data science problem. Moving on quickly. So classification versus regression. We talked about two problems in supervised learning. Your predictive modeling is more about regression. Then you have a numerical variables or categorical variables as your X variables, which means which are your independent variables. And the dependent variable will always be a numerical variable in this scenario. Clear? When you are predicting a numerical variable, you apply a regression. So let's take the example that we talked at length. Classifying whether a customer is a defaulter or not. There are different ways to do it. You can directly use whether somebody is a defaulter or not. Defaulter is equal to 1, non-defaulter is equal to 0. You define that and you can directly apply the model. The other way is, in that scenario, what kind of a problem we are talking about?
Classification, right?
Yes, because that variable is a categorical in nature. Two categories you created, defaulter, non-defaulter. But let's say instead of using a categorical variable like that, I'm going to create a credit score is my dependent variable. From all the variables that I have, I calculate a possible credit score for that guy. What would that credit score would be? A numerical variable.
Yes.
So in that scenario, I will apply a regression. Is it making sense? So when your dependent variable is numerical, you apply regression. When it is categorical, you apply classification. This is the thumb rules that we generally follow. Any questions, guys? Anyone? Right. So let's move on. Now that we talked about these two things, but this session will touch upon regression. So what does regression mean? You are reading what is there on the screen, but I'm generally asking what is the English meaning of regression?
It's it's regressed, right? I mean, regression to mean is a concept in psychology. So
yeah,
regressing actually.
Any changes that has happened or any variations that's happening?
Right. So any changes that are happening, you're tracking of that particular one. But where is that going to? See, I'm telling you, if I make a statement, somebody like you're regressing day by day, is it a logical statement?
Yes, going back to the previous state.
Yeah, exactly.
Yeah.
Regression essentially means going back. That's the exact way. So now, why are we calling this as a regression and going back somewhere? Where are we going back here?
To the mean.
Perfect. That's Prasad. Good one. We are going back to the mean. So the idea is essentially, whatever the data points you are trying to do, what you're trying to do is regress the whole thing towards the mean or the central tendency of that population. That's what we are trying to go back to. So this is a hypothesis. For example, there is this famous book which I studied during my study days called as Basic Econometrics by Damodar Gujarati. If anyone is fond of statistics and reading more on econometrics particularly, this book is a phenomenal book to read. It explains regression in such a beautiful manner to read with. Econometrics by Damodar Gujarati. Okay, so he explains this in the beginning itself, a very interesting concept. As a population, how high we are. You look at Chinese, you look at Indians, you look at US, you look at Swiss folks. What is the average height of each of these people? So as a origin, as a gene, this thing, behavior of our genes and how we tend to behavior, the genes force us to regress towards what is the mean of our civilization. Always. Even if you find a few outliers for whatever reasons, if everyone is taller in your population in general, even there are few people that get born, generally subsequent population will tend to go back towards the mean height of that particular generation or that particular population, civilization. and it is common across any country that you take. You might find a few outliers here and there, but if you take the average height, that represents the mean height of that civilization overall completely. That's what regression is all about in a simplistic terms to look at. But what are we trying to do? You are trying to predict, in this case, the example that I took, the height of that civilization, the mean is what you are trying to predict for a particular person, what height. There are so many factors that could have influenced the height. You take all those factors and predict the average height. That's what the regression is. So for that, you build a linear equation to predict that all the factors that would influence the height and what could be the predicted height or expected height for a new scenario that is likely to come up. That's what a regression means. Is the concept of regression clear?
Yes.
Yeah. Yes. Yes. Yeah.
Okay. So now the second part of the term linear regression. The first one is regression. We understand what regression means. Then what is linear?
The straight line.
Straight line. Yes.
Straight line. But what is straight line with variables? If I say I have a linear relationship between certain things, it is a simple, straightforward relationship, which is generally additive in nature. If I say the variables y, x1, x2, x3 are linearly related, where x1, x2, x3 influence y and they are linearly related, the simplest form of that one could be y is equal to x1 plus x2 plus x3. That's the most simplest linear form of the relationship that ever we can see. If I say y is equal to x1 into x2 plus x3, that's no more linear.
Yeah, you're right.
Right? I am becoming a polynomial or quadratic or some other dimensions will come into play when I'm building that equation. A simple linear equation is always additive in nature. That's why we call it as a linear.
It could be mx1, m1, mc1, ma1, mb1, but it cannot be any other.
No. See, the factors m1, m2 are not the variables. See, I cannot multiply two variables. It's the slope is different. It's the weight factors. That is different. Don't confuse the multiplication of weight and the variable with multiplication of one variable with the other variable. Right? The linear relationship is between the variables.
That's precisely what I'm going to say. The point is the weights can change, but it's still linear, basically, right?
Yes. So in case of linear regression, with a one single explanatory variable that is out there, the linear combination can be expressed as your response or your dependent variable is equal to intercept plus constant into explanatory. Your explanatory is nothing but your independent variable. Constant is your weight or the slope, and this is the equation. So y is equal to c plus mx. That's the equation that we generally go forward. And you all understand the concept of intercept. I assume or I hope I don't need to explain the intercept now, because you would have seen all the preparatory mathematics videos where Mukesh has explained about where the intercept cuts the y-axis. That's the point what we call as an intercept, right?
Yes.
Good. So I'm not touching on that one. Good. So, but one important thing that we need to remember in this whole thing of this thing. So what are we trying to say now? Your explanatory variable and response variable have a kind of a relationship, right? This is being used to predict this. But for that relationship, these two are standard numbers, right? At the end of the day. If let's say there is no explanatory variable, assume that explanatory variable is equal to 0. What happens?
Response equal to intercept.
Response equal to intercept. That's where it is cutting the y-axis as what we have talked. But let's for time being ignore the intercept part and ignore the constant part also for time being. Then response is equal to explanatory, right? When constant is equal to 1, what does that mean? I hypothetically take this part is not there.
And both of them are same, right? Both variables.
Yeah, let's say just this much, and when constant is equal to 1, response is equal to explanatory. What does that mean?
Response is in relation with explanatory.
So if I draw a graph and this is your explanatory and this is your response, how will the graph would be?
It goes to the center, from 0 especially.
It's a 45-degree angle.
Yeah.
Right? Your tan theta or slope is 1 essentially. But this constant or the weight is the one that defines how this line goes, at what point this line goes, what angle. Make sense? So how is this value coming up? What is this slope is being defined as? That is nothing but the correlation between your dependent and independent variables. How are they defined? Are they very linearly defined or not so linearly defined, or linearly defined but not 100%? What extent of relationship is between these two variables? What is that term called? The relationship between a dependent and independent variables that we measure?
Covariance.
We go with correlation.
Correlation.
Right? Okay. Now that it's interesting that you mentioned covariation, covariance. What is the difference between covariance and correlation?
I almost thought they are same.
They are same, but for a minor difference. I'll give that as a homework.
Okay.
Just read. It's an interesting concept because they are exactly the same with a minor difference. What difference it is, when you start reading, you will feel interesting about it. That's why I'm holding myself back from explaining it and making you a little curious to go back and read on that one. Okay, I think we covered correlation in the past, so quickly zip through what the correlation concept at the end of the day. We discussed the correlation formula earlier now. Normally the coefficient of relationship is also called as a correlation, which is for numerical quantities is referred as a Pearson's coefficient. I think I got the covariance and I didn't realize this piece. Coefficient and correlation. Sorry. So basically, if you divide by standard deviation, the covariance, you will get the correlation essentially. Why we define standard deviation? Divide by standard deviation.
Oh, okay, so the formula itself is here. The correlation is equal to covariance by the standard deviation. Okay.
Why? Why do we divide by standard deviation to get to coefficient of this thing? Actually, I thought of that as a question, but now that it is explained here, let me touch upon that for 1 second. Simple. Covariance has units of x and y. It is impacted by the units. The moment you define by the standard deviation also has the units of the same thing. So when you define by standard deviation, now it is unitless. This becomes a coefficient essentially. So it always ranges between -1 and +1.
But covariance does not, right? Yeah. That's
covariance true. Does not. Covariance has units, bound by units essentially. So it is no more coefficient. So when it is not bound by units, it's easy to express and quantify. That's why it is a scale between -1 and +1. Understood? Now, this is a straightforward, clear thing explained in the videos we talked earlier. If there is a linear positive correlation, as we have seen in the previous case, if the correlation is 1 + 1, full correlation between the two variables, you see the line coming like this. If it is a negative correlation, you see the line coming in this form. When there is no, is this correct? When we say there is no correlation, this is how the data would look like, or when data look like this, can we say there is no correlation?
Yeah, because
there is no correlation.
Exactly.
Linear correlation.
A good point. Who said that? Sorry.
Ram here.
Hey Ram, it's an excellent point. There is no linear correlation. What does that mean?
It could be on a plane or something. It could be other forms of.
Excellent. Thank you, sir. There is no linear correlation. That does not mean that the variables are not correlated with each other. There is still a correlation. There could be a different form of correlation between the two, but there is no linear correlation. Let's say, for example, I have a graph like this. Sorry for the x-axis. This is my graph. Is this a linear correlation?
At least the line doesn't look linear, Ram.
But do you think there is a relationship?
Absolutely, yes. Right.
So this is a non-linear relationship exists, but this is a relationship is still there. So this is nothing but the equation for y is equal to x square. So that's what this is. So still there could be places where correlation exists, but it is not linear in those scenarios. So just need to be very sure about this. Could be one of your quiz questions that could come your way about linear correlation. The relationship between two variables is linear correlation is 0, correlation is 0, means no relation. In any kind of scenarios are possible for that. So just as a point to keep in mind, I thought of bringing that. Good. So let's move on to the next point on this. Now, when you say you have two variables, x and y, and there is a relationship. Now let's say the first thing that what we do is, for any given data, the relationship between 2 points, you define that as a y is equal to f of x, and you plot that on a plane, essentially. So you plot this, you first draw a scatter plot, and you figure out what is the data trend looks like. Don't bother even about the line first. See, first look at what is the data trends. That gives you the correlation between these two variables, which visually you can inspect. Then you can start building a trend line. Building this trend line is our objective. That's what your regression equation is. Once you build a regression equation, that regression equation is going to form this line that passes through all these points. Now, this is a very important concept to keep in mind. When we draw a line in an ideal scenario, what should be the perfect place? Every point that is out there should fall on this regression line. Is that making sense?
Right, yes. Yeah.
Right. So let's say, for example, there are multiple examples that Mukesh covered in the class, and let's say one of the examples we pull, and let's say we built this graph. If I have to say an equation, y is equal to x plus 2, an equation I have just given simply. And if I start plotting that particular one, so when I start the graph and when I plot the points and draw a line, should every point fall on that line for every value of y, for every value of that equation result of, let's say x is equal to 1, y is equal to 3, x is equal to 0, y is equal to 2. So it intercepts at 2 and goes on 1, 1, 1, 1 kind of a thing. It goes on the same line. You're following me? So let's say I draw this chart. This is my line. Y is equal to x plus 2. For every point of x, there is a y that is defined. So when I take any value for x, it should fall on this line definitely, right? That's the ideal scenario. All these points would start on this line only. But what happens when this kind of a thing? There are some points falling on the line, some points falling above the line, some points falling below the line. What is the difference between this and this? Why do we see this scenario?
I mean, we are trying to make the best fit line in this case. And another case which you explained is you're trying to draw a line based on an equation.
Good point. But there is one subtle difference that is out between these two. This is called as linear deterministic model. This is called as linear probabilistic model. You're understanding? So here there is no element of uncertainty here. You know everything. For a given value of x, you know for a given value of y exists. For a given x, you know a certain y exists. And if x changes, y has to change correspondingly, which follows this equation. But in this scenario, for this particular one, if I look at here, for the same given x, there are 2 points that are lying, which leads to me a uncertainty. You're getting what I'm saying? And in this case, for the same given y value, I have for 2 different x's, I am getting the same y value. Assuming that there are 2 dots here. If not, we can ignore. Hypothetically, I'm saying, or take this one. as an example. So this is essentially somebody would have probabilistically said that for this given x, this is the value of y, or for this given x, this is also the same value of y that I am getting. That's why 2 points are plotted for 2 different x's, same y is being plotted. So there is an element of probability estimation is happening here. That's why this is called as a linear probabilistic model. So in this scenario, your equation will no more look like this. There is something coming in here into play. Your epsilon, sorry, forget that bottom line. A simple epsilon or alpha, C, whatever, there are different terms that are being used there for this one. So there is this unexplained error. So when your dependent variable is not exactly equal to your intercept plus constant into explanatory variable, whatever this is, and there is a small variation that exists, this is the difference that exists. This is what is called as residual.
Is epsilon is equivalent to the residual error, right?
Yes, it's a consolidated residual error for the whole equation. Not just for one individual observation. So every individual observation has its own residual error. So this is the total unexplained variance. Look at that particular way explanation. This is the so if this is not equal, there is some component of this response that is not explained by the explanatory variables you are looking at. All that is summed up into this unexplained error. Is it making sense? That's why there is an element of probability that is influencing this calculation errors. That's why this model is called as a linear probabilistic model. Whereas when everything is equal to perfectly the values between x and y, then it becomes a linear deterministic model. Okay. Now, how do we calculate that errors? That epsilon that we talked about, how do we calculate? So for each of these line, so the line is the best estimated line which is formed by the equation that you have created. Based on that, the best fit, you define a line. Then from you calculate the distance between that line and each of the points that exists. This one and this one. Yeah. So this is the equation. The line is explaining y equal to mx plus b. What we are talking about. Let's say all these are the points that are there. So now this blue bar that we see is x bar, the mean of all the x values. Y bar is the mean of all y values. Let's say that intersects at this point. So there is only one point where it is possible the x bar and y bar intersect with the line, this particular one. So from that point, you take the reference point and look at each of the points. Then we see the variation of each of these things. Let's say if this line is this, you calculate the error like this. So I'm not reading into that. I'll come to that later, the R square part, what is being explained there. We'll come to that. Let's understand this error part first. So let's say we are taking just one example. So in this line, we'll take one example somewhere, some point is there, and we're calculating that. So this is your y equal to mx plus c or y equal to ax plus b, whatever the equation is. We are coming to this particular equation, and there is one data point which is not exactly falling on the line but lying somewhere above, or it could fall below this one also, somewhere, anywhere that is possible. So now how much gap is between? So ideally, if this point has to fall on the line, it would have fallen here, but this point is actual original point is the actual given data is here. But when you calculate for this given x, the y value is coming out to be here. So the distance between this P1, where the actual data point that is there, versus the predicted data point that is there, is called the residual for this particular point. This particular x, that is the residual. This is called as the residual error, SSE. Is the residual error that is out there. Are you getting what residual error means?
Difference between actual value and expected value.
According to the regression line.
Model, exactly. Yeah.
Model. That difference is the residual error. But this value for this given x, what should have been the y bar? Essentially here, this line. This is where the regression line is intersecting with the y bar. So this is the value. So the regression line versus the average value, there is a difference again. The difference between the regression value calculated versus the average value of the y variable, this is called as a regression error. So there are two errors coming. One, where is the actual data point? Where is your regression line telling? And what is the average of your given data? These three are the three important things. If it is a linear deterministic model, that what we talked about LDM in the previous scenario, all these three would be around the same place. Logically. Or y bar could be different, sorry. These two would be around the same place, whereas y bar only should be the error that exists. So if you actually look at, you cannot control this error because y bar and can intersect at only one point and the points can vary completely across the line. So this error you cannot control, this regression error. Whereas if your variable can predict exactly, you can control the residual error. Making sense, folks? Or everything bouncing off the head?
The y bar error, the perceived error, has already been absorbed by the model, right?
Yes, the model. So we'll come to that. So the y bar error is y bar at any given point, y bar intersects at only one point on the whole regression line. Let's say if your y bar has been here, this line, it would have intersected somewhere here.
Right, yeah.
But still for the rest of the points, the error would still exist. So you cannot control the regression error totally. And that regression error for some points, it could be negative, for some points, it could be positive, because based on where it is occurring. It keeps on happening. But so essentially you cannot control your error related to y bar. But this is only the thing that you can control. The better accuracy you can get with your x value, this error will reduce. So how do you reduce this error now?
Changing the lines, probably.
Yes, getting the best fit line. So
Yeah, right.
What is the best fit line? Instead of this line, maybe some other line like this would have made a more sense. This is a hypothetical thing. Maybe a line going like this would have reduced the error, or maybe a line going like this would have reduced the error even less, right?
Right.
So if this line is making better sense in terms of reducing the error all across, it's not just with this point. That's what we need to keep in mind. So what are we trying to do when we are fitting this best fit line means what? Now let's go back to the previous slide. When we talked of a best fit line here, what are we talking? What is the best fit that we mean here?
Where the error is minimum, right?
Where the error is minimum across all points. It's not
Across
just
all.
one point alone. So if I take this line drawn, if I take any point, there is no other line that gives less error compared to this particular line.
Right, makes sense.
So if I take this error from this point to this line to this point that is out there, if I draw any other line, the overall error that is coming out will be the minimum. Sum of all errors, residual errors that comes out, the SSE, the sum of squares of residual errors that is coming out would be at its minimum when this line is drawn. For any other line, that error would increase. That's the best fit line. You understand the concept of best fit line? That's why it is called as a regression line. It is representing the mean that we talked about, the mean height of the civilization, mean value of the civilization, population, whatever you call. This is coming closer to that. There could be some outliers that are out there. Somebody could be less height, somebody could be more height, but this line represents that best thing that is out there. Yeah. So how do you define this coefficient? This line is the best fit line. How do you define that particular line is the best fit line? how do we say this line is the best fit line and the one that I have drawn is not the best fit? How do we go with that particular thing? So to calculate that, we come up with a particular metric called R square. Folks, following me?
Yes.
Yes, sir.
Yeah. So coefficient of R square. This is called as the coefficient of determinant of your regression model. So when your line is best fit with least squares, with least of sum of squares values across all data points that is out there, compared to this one, this R square approaches 1.
Right.
When your R square is closer to 1, that means that this line is the best possible fit that you are getting in. That's the ideal scenario. But in majority of the situations, that does not happen because of the term that I explained earlier, the unexplained variance. There is always something that you cannot explain, because of which there's a gap between the observed value versus a predicted value. And how less this value explains that R square. If your R square is 0.8, 0.9 kind of a thing, which means that your explanatory variables are pretty much able to explain what this dependent variable is all about.
So Ram, R square when you say here, is it basically R into R, or is it a summation of all the squares, or?
Yes, there is a formula to that. So we'll take that one through an example. We'll come to that. So R square is basically called as a coefficient of determinant. You see, in a linear regression, simple linear regression where there is one variable, it can be construed as good as just square root of square of R, which is a correlation coefficient between your dependent variable and independent variable. But when you get into multiple correlation, multiple linear regression where multiple variables, explanatory variables are there, then it's not just between this and this, then there are multiple scenarios possible, right? So your y into x1, y x2, y x3, all r1s and r2s are possible, right? So there is an interaction effect out of all of those things. So that's why we take into account the formula called the coefficient of determinant formula, which is taken based on the sum of squares of residuals. See, it exactly goes in this formula. We look at the formula, then we'll understand. But it takes multiple variable coefficient of determinant. It takes all variables into account and then calculate. That's what R square is. So that R square explains how good your model is. As R square value gets closer or inches towards 1, your model is supposed to be a best fit. Are we clear so far?
Yeah.
Good. So let's move on from this one. So these are the same terms. This explains P1 is the original data point, which is your data point given by the data set. P2 is the estimated data point. Y bar is this particular one, what all we talked about. I'm just reading through what is there on the slide. So now you have two types of errors. One is SSE, which is your residual error. SSR is regression error. So these two types of errors together called as total error that is possible in your regression model. Total error is equal to residual error plus regression error. So there is one term that you need to keep in mind. In this regression model, the equation that we saw here, this whole piece, sorry, I removed the intercept part earlier. Assume that the intercept is there. So the intercept plus constant explanatory, this is one part of the equation. This is the other part of the equation, right? So this part is called as controllable. This part is uncontrollable. You can control this piece because by varying your x values, by varying your constants, by calculating different predictors, everything, you can control this particular one. This is a reducible error because by controlling this particular one, you can reduce the gap between your y and your dependents and independents. But how much ever you do, you cannot control this. This is irreducible error. So the two components are important to keep in mind. That's why because you cannot control this particular piece, you always try and control this particular one. That's what essentially this model is also talking about. So that this reducible error, this SSC is the reducible error. This is what is controllable for us. This is controllable, whereas this is uncontrollable. You cannot control this. So this SST can be as minimum as possible only when SST is equal to this regression error. Total error is equal to regression error. That means you don't have any residual errors. That's the best scenario for us to possible get. And in that scenario, your R square will become 1. Any questions on this? Just blown over the top. No confusion. Everything understood. Guys, honest.
I get confused with the R square.
Okay, so in simple terms, let's say simple terms. So now we understand. Everyone, please, anyone who has any doubts on this one, just raise a question right now. I'm trying to summarize and put everything in simple terms. So when you draw your regression line, there are 2 different types of errors that are possible. One is a residual error. Second one is a regression error. Are we clear with these two?
That's pretty clear.
Right?
Yes.
So what is residual error?
Difference between the actual data
the actual or observed value versus the predicted value based on your regression equation.
Right.
The difference between these two is your residual error. Understood?
Yes.
Now you have your y variable. The average of that y value, take all the values and just calculate the average, y average of that particular one. Then with every given point, that y variable will have some difference.
Yes.
Right? So that those all differences are called as regression errors with respect to each point. When you add up all of those things, it becomes a summation of all regression errors. The regression error is nothing but the y bar minus where your regression line is talking about. Your y bar, y should have been.
So something similar to how we calculate variance, right?
Variance, essentially, yes. No, the variance ideally would have been this observed value versus predicted value, this thing. But this is why the regression error. This regression line, whatever the value is telling versus this y bar, that's the regression error.
Got it. Right.
2 points. Is everyone with me on this so far? Now, the simple thing to remember is you cannot control regression error. You can control residual error. Whatever you do, you cannot control regression error.
Right.
All you can do is control your residual error. And for a regression line, regression equation, the total error is nothing but sum of your residual error plus regression error. Because you cannot control regression error, when your total error is nothing but your regression error, then your model is the best fit possible that is out there.
Right. Yes.
And when that scenario exists, your model is the best model and its coefficient of determinant. Determinant is nothing but determining how good and robust your model is. That is indicated by a coefficient value. That coefficient value ranges between 0 and 1, your R square value. That is represented by R square. Your R square ranges between 0 and 1. When R square is equal to 0 means this line not at all explains the given data points. When R square is equal to 1, except for regression error which is given, there is no residual error that is possible.
Got it.
That's all the whole regression equation at the back end is. Now when we calculate this one manually, we'll see through one quick example and we'll see, you'll understand how we are calculating each of these things. So the idea is all about calculating these errors and then through that one calculate your beta coefficients, your intercept and coefficients of this particular one. That's all your regression at the end of the day. See, there are more concepts for us to look at, like bias, variance, when does bias come in, when does a variance come in and everything, but I won't go into them. When we look at the next module, essentially I'm getting into the data, calculating, understanding variance and bias will come into play when we get a little deeper. This is a basic concept of how a regression works. And regression is the simplest of the models of all the things that exist. Okay. Anyone? I know Prasad has been saying that he understood now. Anyone else has questions All right, thank you. But just feel free to ask me if you have a question or not understood. Okay, so simple advantages, disadvantages. I think we have already discussed some of this. What are the advantages of linear regression? It is a simple one I just mentioned, and implement and easier to interpret the outputs. Because you calculate that one, you calculate your betas, and you say that this is the impact of my explanatory variable on my dependent variable. It's a straightforward explanation. That's why it's easy to interpret, and how much bearing this have on that one. Disadvantages, the default assumption is that there is a linear relationship between your dependent variable and independent variable. For example, if you take the scenario of the line that I draw earlier, y is equal to 2x square plus 3. Is that a linear equation? Linear variable, linear?
2x plus 3, yes, it's linear.
No, y equal to
No,
2x
the
square
is
plus
not.
3.
No, for sure not. It's
For
not.
sure not, because it is quadratic. The moment we get into quadratic, that is not linear. But I cannot draw a linear equation between those two, because that equation would go somewhere like this. There is no linear. So the moment you apply a linear, just because you can apply a model on that particular data, you apply it, it does not give you any results. So you need to think about whether there is a linear relationship between the variables or not. Model by default assumes that it has. Then if you have outliers, it will have a huge bearing on the regression. What does the outliers mean? So let's say, for example, this point, this y bar is, let's say there is one data point sitting somewhere here. This y bar will be very much influenced by this outlier that is sitting out there. Then your regression error will go for a toss. As the regression error increases, your epsilon increases. When this increases, the explanatory power of your independent variables goes down. Correspondingly, your R square goes down, which means the model does not get a best fit line. You followed that?
Yeah, right. Is there any quantifiable measure to determine the outlier run? Like, say, it's far away from mean, but
Go back to your initial classes of box plot. So now when you do a regression, now this is part of the pre-processing, Prasad. When we talked of pre-processing earlier, take all variables and identify which variables have outliers and is there an outlier treatment that you need to do. Do that and come back to your data, then your model fits automatically much better than what it has been.
Got it. Makes sense, yeah.
Yeah, that's where the pre-processing will come into picture.
Okay.
So next, we'll do a small case study that is out there. It should not take long because it's very simple, straightforward already, this thing. And I'll forward this material. There is one link on this one. This is the case study. Okay, so everything is solved here. But this link is what you should look at. Don't bother too much about what is explained here. This link on this one, sorry, takes you to this page. Yeah, this page. Simple linear regression 1, least squares estimation. This is exactly the same problem that is out there. I'll run you through that one example that is out there quickly. It shouldn't take long. But when you read through, you have multiple examples that you can think through and how to look at. There are 3, 4, or 4, 5 case studies given. You should just read through how the formulas work and everything. But what this problem essentially is talking about, so this talks about what I called about linear deterministic model versus linear probabilistic model. What is the difference? If the equation is just right like this, it's a deterministic model. When you get this epsilon kind of a thing, this becomes a probabilistic model because there is a random component that is coming into that particular one. It explains all of this. Spend a little time to read through, you'll understand easily. Now coming to what the problem is. So there is this coffee sales and shelf space. So in a particular shop, in a particular store, we all see, right? People arrange products by shelf space, and different producers, manufacturers, or firms have their own shelf space allocated for their products. So this particular lady who is a marketing manager here want to understand the relationship between the shelf space for her product and the weekly sales that are happening in a given place, in a given supermarket. So there are some assumptions that are made to assume that everything is simple. Life is not that simple, but it is. So when marketers are well aware of the concept of compulsive purchases, because when it is in the line of sight, I can easily see I want to pick and test that particular one. If it is somewhere at the bottom or somewhere at the top, maybe I won't so immediately look at that. That's the hypothesis behind that. Now what she is looking at is, she believes that in the range of 3 feet height to 9 feet height, the mean weekly sales are linearly related to the width of the shelf space. So if the width of the shelf space is 3 feet, sales is X. If the width of that particular one is 9 feet, this is X plus something. It could be significant, and that varies linearly between 3 and 6. 3 to 4 it increases, 4 to 5 it increases, the sales increases. That's what her hypothesis is, and she wants to test that. So to test that piece, what she has done essentially, you can read through. I'm giving simply the problem. To test that scenario, what she has essentially done is she has taken 3 scenarios: shelf space of 3 feet, 6 feet, and 9 feet. She tested this randomly, not as a constant thing. She randomly tested across 12 weeks, each week coming up with a different space. 1 week 6 feet space, 1 week 3 feet, 6 week 9 feet, 3 feet, like that. She tested this for 12 weeks. For each week, she identified what is the sales of her product across each of this week. That's the data that she has. So what did we do? This is all the data that we have. Now we have to come up with a regression equation which tells there is a linear relationship between the shelf space and weekly sales. Is that clear? Linear relationship is nothing but a regression equation.
Yes.
Right? So that's what she is testing. As we discussed in the steps, first identify the right data. We identified shelf space and weekly sales that are there. Then draw a scatter plot. This is the scatter plot that is drawn. So sales on y-axis, space, shelf space on x-axis. Whenever she has a 3 feet, she has identified 4 points. 6 feet, 4 points. 9 feet, 4 points. Visually, can we see that higher the shelf space, higher the sales?
Yeah, visually, yes.
Right? So it's nothing but drawing a straight line. If I draw a line like this should go like this. Yeah. So that there is a positive correlation between space and sales. 1 point is taken. Now, given that, she is coming up with an equation. So note that while there is some variance among the weekly sales at 369, what is the best line that expresses? We have to come up with that line, which is y bar is equal to beta naught plus beta 1 into x. B0, B1, beta naught, beta 1, anything is fine. So this is a straightforward equation. We are not, for this point, at least we are considering a unexplained variance, whatever it is. We left that. So when you are actually getting into mathematical equations, you tend to ignore that. You assume that that component exists. Only when you write mathematically, you mention that unexplained variance term that is there, right? Now we have to choose B0, B1 such that these values fit in pretty much into these data values. That's how you calculate the coefficients. All our problem right now is to calculate these coefficients in the right way. So how should these coefficients be calculated? What should beta 0, beta 1 be? So when you get the correct beta 0 and beta 1, for any given value of x, beta 0 plus beta 1 into x should be equal to y bar. That's how the beta 0, beta 1 value should come in. Understanding that?
Yeah.
Everyone has gone to sleep.
It's the same equation like y is equal to mx plus c, right?
Yes, right, good. So we'd like to minimize that particular error that exists. So the error is calculated as the sum of the squared error. This is what we want to minimize. So the SSE is calculated by these formulas. So
SSC is the residual, right, Ram?
SSE is the residual errors. Exactly. This is the residual error. SSR is your regression error. So here we are calculating the, so see, why we won't calculate regression error at all by any means. Why?
It's already absorbed in the model. So
one, and you cannot control that error. What you cannot control, you don't want to calculate or bother about it.
Okay.
So you will bother about only what you can control. That's why you are always focused on SSE. Right? Now the SSE is calculated by this particular formula. Sigma I is equal to 1, yi minus y bar. So for each of the points that is there for the equation, so you calculate from the expected line versus what is the value, predicted value versus average value for that particular one. For each of the points, you start calculating that one. So this is yi minus y hat I. So y hat I is nothing but this formula what we calculated. Y hat is equal to B naught plus B1x. If I say Y hat I, this becomes B naught plus B1 into Xi for every I value. So that is just replaced. Y hat I is replaced by B naught plus B1 Xi. This is what is calculated. So then you summarize this equation. So B1 is equal to this covariance value essentially divided by SSX. So this sum of squares of X and Y, this is a cross product. So basically if you look at this table, it has been converted into this form. So you have to do this exercise basically. That's what has been done. So your week, 12 weeks, space, and Y. These are X and Y variables. So you calculate X square, you calculate XY, you calculate Y square. So this is the squares values. This is the XY. This is the product of the correlation product. Covariance purpose, you calculate all these three. The formula of covariance. So you simply remember these three formulas that are there. So don't bother about deductions. You need to remember. That's why this says. So they are not very intuitive to remember. You can calculate. If you convert this formula, you will come to this particular one. SSX, SSXY, SSYY. SSXX is nothing but X square only. So that's what we are calculating here. So beta 1 is nothing but SSXY by SSXX. And beta naught, you will calculate by substituting this B1 value here. Yeah, understanding?
I think we need to read this and practice it.
Yeah, so basically two simple things. B1, B0 are the two values to be calculated. B1 is nothing but sum of squares of XX by sum of squares of XY by sum of squares of XX.
Yeah, right.
B0 is equal to, normally here if I have to calculate B0, what is it? B0 is equal to Y hat minus
Y
B1
minus
B1x, right? That's what I am doing. B0 is equal to Y bar minus beta 1 into X bar. What is Y bar? Adding all, this is the mean of Y. Simple mathematical representation. The sigma is equal to 1 to n yi by n. This is the Y bar. Minus B1 into X bar is nothing but the X value. This is what B0 is. Simply calculated. Beta 1 is the interesting part. If you look at this, this is coming through this SSE value. And there is an alternative way to calculate that, which is coming through covariance. That's why covariance is important. We talked about covariance. Covariance of X and Y is nothing but sigma is equal to 1, Xi minus X bar into Yi minus Y bar by n minus 1, which is equal to SSXY by n minus 1. And Sx square is equal to Xi minus X bar whole square by n minus 1, which is SSXX by n minus 1. So covariance divided by Sx square is nothing but your B1. The same
formula, right?
That's the same formula. It's all about, guys, last point. You don't need to remember any of these formulas. Your Python program throws out all these values. This is just a mathematical concept going behind. All I'm trying to explain is how is this, your residual errors is coming into play, how that is calculated, and how is that is mathematically calculated in a physical way. That's what you need to remember for this formula. Making sense? So you get your B1 is equal to through this formula, B0 is equal to this formula. So you apply those values on this formula. You calculate SSX X is equal to 72, SSXY is equal to 2490, SSYY is equal to this particular value. Now B1 is equal to SSXY by SSXX, which is 2490 by 72, this much. B0 is equal to sigma y by n minus B1 into sigma x by n. So this becomes 6185 by 92, 12. So this is a straightforward calculations. And the B1 you calculate here, you just substitute here. You get 307. That's how you formulate your regression equation. Following how we created a regression equation. Now you have this regression equation and you fit the value, and you can test this by substituting any value between 3 and 9 on this one. If you substitute 3, 4, 5, 6, 7, because these two values are fixed, this is a linear equation that forms. And the equation, the line essentially would go through somewhere from here to here like this. That's what this problem is. And like this problem, there are other problems, like how do you calculate the stock beta, stock values? Then there is another problem talking about the cost functions for a hosiery mill. Then there is other problem that is talking about coefficients, the same thing. See, this is the line I was talking about, how it goes.
Well, so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.